A very good morning, good afternoon, or indeed good evening, depending on where in the world you are, and welcome to this webinar, Fuel Cells, Addressing the Key Technical Challenges. This webinar is part of Riviera's Maritime Hybrid, Electric and Fuel Cells webinar week. It will be 45 minutes in duration and is held in association with our premier partners, Alsteen, General Electric, and Nedstack. Now, ladies and gentlemen, before we get underway, I'm going to share with you some key information that will support you in getting the most out of today's webinar. First of all, please be assured we will send you the recording after transmission. Please do submit your questions at any time because we will do Q&A throughout the webinar. And any questions that we don't get to, we will come back to you in writing 1 week after broadcast. So there's every reason for you to get involved and to send those questions through. Please stay tuned into the end so you don't miss out. I guarantee over the next 45 minutes, you're going to receive powerful, original, and exclusive insights that can really benefit your business. So please stay tuned. And finally, please complete the exit survey, and in return, we'll send you the presentations. Let me say a word or two about your hosts, Riviera Maritime Media. Riviera is a maritime and offshore information specialist active in 4 areas: news, events, jobs, and data. Should you wish to know more, please visit the dedicated website www.rivieramm.com. About time I introduce myself. This is me, Edwin. I'm Edwin Lampert, Head of Content at Riviera Maritime Media, and I'll be your moderator today. So let's look at today's agenda. We'll be variously looking at safety, hydrogen storage and fuel cell system. We'll look at vessel layout and space management considerations. We'll look at fuel cell technologies for maritime application. The 3 R's, refurbishing, reusing, and reclaiming fuel cell components, as well as fuel cell power requirements for different classes of ship. Now let me share with you our running order, or in other words, how it's going to go. Presentations will be run consecutively and then followed by open discussion. As you know, please submit your questions at any time because we do Q&A throughout the webinar. At the end of the webinar, we will share key takeaways and conclusions, and we'll also preview what's next. Time to meet our panelists. I'm delighted that we have Ko Struve. He is product manager with Alsteen Design and Solutions. Next up will be Renaud Cornu. He is senior sales passenger vessels with GE Power Conversion. And completing our lineup, I'm delighted that we have Raoul van der Pas. He is chief commercial officer with Nedstack. During the course of the next 45 minutes, we'll find time for a poll or two, which you, dear audience, will be able to participate in. And as you know, please keep those questions coming, submit them via the webinar messenger. Well, more than enough from me, ladies and gentlemen. It's high time we heard from the experts. So at this juncture, I'm going to hand over to Ko. So Ko, good sir, as and when you're ready, the floor, as they say, is yours.
Thank you, Edwin. Let's start with a question. Which came first, the chicken or the egg? Does anyone actually know? I think it's the same with hydrogen bunker facilities. A hydrogen-fueled vessel is useless, but we need those ships to build our experience and prove it works, and also sort of ignite the infrastructure development. We at Alsteen design and build offshore vessels, and I will show you how we can solve the chicken and the egg problem of hydrogen infrastructure. Besides the hydrogen infrastructure, we see 3 other challenges to successfully adopt hydrogen as a zero-emission fuel for ships. Regulations are under development, and yes, we are in discussion with class and authorities. And for green hydrogen projects, multiple have been announced in recent years, like the Port of Rotterdam, Zeebrugge, and Denmark are all showing new initiatives. Also, many governments have expressed their intention to invest in zero-emission technology. So that leaves actually how to solve the infrastructure problem the coming years. We actually started the development of the zero-emission offshore vessel as a sort of case study of the state-of-the-art hydrogen technology. We just wanted to see if it could already work on the drawing board with the rapid developments in fuel technology and electric power systems. We use the available ITF code and our experience with LNG-fueled vessels to design a safe and first truly zero-emission offshore vessel. And yes, the initial cost estimates are considerable, but at roughly 25% additional investment, the vessel sort of seems acceptable, especially as most of the additional cost can be subsidized. Well, fuel cost is a bit of another topic. I will not go into much detail here on that. But how do we make such a vessel work without any hydrogen infrastructure? Back to the chicken and the egg dilemma. We selected a flexible containerized gas storage system on the aft deck. The current capacity of the storage system limits the range to probably 4 or 5 days in zero emission mode, but it allows the vessel to be independent of any hydrogen bunker facilities. So the hydrogen gas can be refilled by trucks at the quayside, or the storage containers can actually be lifted off the aft deck and shipped back to the hydrogen plant for refilling. This is especially useful as the local port authorities will not allow any hydrogen bunkering in their port yet. Well, this already available solution bridges the gap towards future hydrogen regulations and infrastructure. Of course, 4 to 5 days is not really a tremendous range, so to extend the endurance of the vessel, we adopted a dual fuel solution. So the 2 megawatts of electric power generated by its PEM fuel cells is supported by 5.5 megawatts of more conventional diesel electric system. This enables the vessel to fall back on its diesel engines for extended missions and capabilities. Of course, the hydrogen can also be used when entering port and being moored, eliminating any local emissions in sensitive areas or inside cities. So how do we get the chicken and the egg both in the end? Well, to enhance the zero emission range, the first step would be swapping the gas storage of the liquid hydrogen containers. Cryogenic liquid hydrogen triples the amount of hydrogen per volume, and these containers will probably become commercially available in the coming 2, 3, 4, 5 years, and would actually extend the range to probably around 2 weeks without any modifications to the vessel, and maintaining the bunker flexibility of a containerized system. When port bunker facilities for liquid hydrogen become available, the large project stores under the main deck can be used to install 2 large liquid hydrogen storage tanks. The zero emission endurance will probably increase to close to a month, and the full work deck will become available for offshore operations. Well, this final step would be a vessel fully powered by hydrogen, but it's only feasible when liquid hydrogen is available worldwide in any port. Until then, the fuel flexibility of this Ulstein design will be a necessity in the transition towards an hydrogen economy. So now I will leave it to my friends of GE and Netstek to tell you more about the actual technology.
Thank you very much indeed, Co. Much appreciated. Great job. And testament to that is a volume of questions that have been generated. Ladies and gentlemen, please do keep those questions coming. At this juncture, I hand over to Renaud. So as and when you're ready, good sir, the floor is yours.
Thank you, Edwin. Hello, everybody. Nice to have you with us today. The world needs green solutions. Shipping industry won't be able to cope with all this just looking at SOx and NOx emissions with emission controlled areas. We also need to tackle greenhouse gas emissions. LNG won't do the trick. IMO is asking us to reduce by half emissions by 2050 compared to 2008. In 2023, they will reassess the situation and may even set even harsher targets. So GE works on zero emission solutions. We need zero emission power and propulsion plant solutions. In that goal, we have come to the conclusion that low temperature proton exchange membrane fuel cells powered by hydrogen are the most mature solutions. Now, maritime industry is not the automotive. A ship is to sail 30 to 40 years and requires 4 megawatt power plants, when a car is driven 7 years and look for kilowatt systems. Netstak is the right choice in that regard. They have megawatt power plants in operation with 70,000 hours of operation. They have maritime experience, and we are working with them on maritime developments. That's why GE is very proud to have an exclusive partnership with Netstak. As I said, it's been already a few years since we work on this. We have now developed a 2 megawatt fuel cell power installation. We are looking into end of life here. Indeed, there is one commonality between fuel cells and batteries, is that over time, the power available reduces bit by bit. So it is very important to consider properly the design and the sizing of the system. Here also you can see the typical scope of supply. We have transformers and converters out of G-Power Conversion Maritime portfolio, and we have the fuel cells and its balance of plant. G has decided to really build on our rugged and sea-proven advanced power electronics. Here you see a typical single line diagram of a 2 megawatt fuel cell power installation. We need to really tackle all the maritime requirements. We need power density, we need redundancy, we need serviceability, and we need availability. And all this needs to consider that fuel cells are not gensets, nor batteries, nor solar panels, for instance. Though there are specific challenges to tackle. We need to have a specific fuel cell protection strategy. We need to have a specific selectivity strategy. Also, fuel cells have intrinsic qualities that require to be considered. There are current ripples, for instance, or short circuit specific behavior. Now, one of the main choices we made technically is to have a galvanic insulation. Indeed, fuel cells generate electrons and protons, so we need to ensure the proper subsystem insulation, and we need to avoid common modes so that we can guarantee FCPI availability and safe operations. So now we started to work also on a 3 megawatt electrical power plant out of fuel cells. Objective is to keep gaining in compactness without any compromise on redundancy, safe operation, serviceability, and availability. Now, looking at the system as a whole, again, there are specifics. Power management system is to be developed specifically for this. Indeed, we need to guarantee proton exchange membrane lifetime. We need to guarantee a system efficiency. Now that we have a 2 megawatt fuel cell power installation and a 3 megawatt under development, the nice thing about this is that we'll be able to come up with a wide range of hybrid solutions. We'll be able to combine those 2 and 3 megawatt bricks, let's say, with batteries, with gensets, and we'll be able to address a wide range of solutions for the shipping industry. It's all a matter of will now. So I pass over to Edwin back. Thank you all. Bye-bye.
Thank you very much indeed. Not bye-bye, but au revoir. We will see you again in the Q&A and poll section for sure. But more immediately, I look forward to the comments as we do of Raoul van der Pas. Raoul, as and when you're ready, good sir, the floor is yours.
Thank you very much indeed, Edwin. Thank you very much to my colleagues, Renaud and Co. By now we learned what a zero-emission ship looks like, and we've learned how fuel cells integrate within a vessel propulsion system. I think this is the time where we start to wonder what exactly is a fuel cell and what makes a fuel cell maritime fit. A fuel cell is an electrochemical reactor in which a fuel, in the case of a PEM fuel cell being hydrogen, reacts in an electrochemical manner with an oxidant, being oxygen in air. What a fuel cell does is it generates electricity, it produces ultra pure water, and it generates heat, and it does that without producing any byproducts. So fuel cells are electrochemical reactors, and opposed to batteries, they are not accumulators, which is to say that we need a system around them to provide the media at the right quality and to condition the power in the proper manner and in a very safe and maritime proof way, as Renaud already explained. Now, what makes a PEM fuel cell maritime fit? How does that characterize these kind of units? And here I think the key words are robustness and long life, as well as a very mature safety concept. So from a lifetime perspective, fuel cells need to work with the 5-year dry dock periods that are so typical in the maritime domain. So developing to be serviceable, to be swappable, to be refurbishable, and most of all, to have a decent time between service intervals, that is very fundamental. And aside of that, the safety concept that is required for the maritime domain needs to be very mature, needs to be proven, and needs to be class accepted. And this is how we've tried to tailor that into our product. But as said before, a fuel cell is just a reactor. It needs a so-called balance of plant around it, which is not only a power conversion system, it includes a lot of other equipments, instruments, and valves. So a PEM fuel cell is just part of a fuel cell power system, which is part of a fuel cell power installation. So by extension, a fuel cell power system needs to be maritime proof as well, and needs to be tailored to not only fit the maritime supply chain, but also to meet all of the other requirements of the maritime intended use. We try to solve that by staying away from using automotive grade components, which are typically fit for a few thousand running hours, but to rely on the maritime and industrial supply chain for creating a balance of plant that can last for hundreds of thousands of running hours. And that indeed is fit for 5-year dry dock periods in terms of overhaul. Most importantly, we have relied on what we call a quasi-atmospheric hydrogen system, which is to say that we try to keep all of the hydrogen as much as possible in the fuel compartment where it's safe, which is a hazardous zone, and which protects the hydrogen from any forms of combustion. So these systems, they run on quasi-atmospheric pressure. They are fit for 5-year dry dock periods and for overhauls, and they meet class conformity. All of that in a compact manner, which allows for meeting the power density requirements of the maritime domain. And this interacting from an electrical perspective with C-proven power conversion systems as the ones of General Electric. This is the way how we've developed fuel cell systems to be fit for the maritime domain. And I think the good thing is that we didn't start doing that yesterday. Our first class approval were done in the year 2012. This was the first time we had deployed fuel cell systems in a passenger vessel. And ever since, we've been working on the industrialization, seaworthiness verification, and I'm very much confident that this is the time we are ready for deployment. And that is the message I want to share with you today. So back to you, Edwin.
Thank you very much indeed, gentlemen. Fantastic jobs all round. Testament to that is the volume of questions that we've received. Please do keep those questions coming. Just while we head up the questions, I'd like to come to your audience with a poll or two, so stand by. The first poll question will be visible on your screens. It asks, when will the maritime industry have to exclusively order zero emission vessels to meet IMO 2050 goals? Great question. You can see in front of you, ladies and gents, a range of options. I appreciate you can't see the results. I can, and I share the results in an article after the webinar, but what I can tell you is around 50% of you are saying 2030, about 27% are saying 2025, and then there's an even split of the balance between now and don't know. Actually, more of you don't know versus now. But as I say, full results in an article after the webinar. Let me give you one more poll and then we'll start tackling as many of those questions as we can. Keep them coming, of course. So here we go. Poll question number 2 is, what is H2 fuel cell power and propulsion systems major hurdle today? What is hydrogen fuel cell power and propulsion systems major hurdle today? Once again, you can see a range of options. The most popular response at the moment is totally new ships and systems. In fact, it's not, it's infrastructure that's overtaken. Then it's cost, safety, and then lagging behind competing fuels and regulations. Clear majority for infrastructure. The full results, as you know, in an article after the webinar. Right, ladies and gents, let us turn our attention to those all important questions. So dear panel, please ready yourself because the first one is heading your way. It states, power density is often a concern for higher powered fuel cell systems, particularly when considering the hydrogen fuel storage and its supporting systems on board. How can this be overcome? Who'd like to have a crack at that one?
I can have a first.
Renaud? Sure.
Just one. Yeah. There is a message I would like to say on this, and it's a very important one. Once you decide to go toward a new solution, you need to come up with a new ship design. So it is very important to know what you need and start from scratch. If you want to modify an existing vessel, it's going to be almost impossible. I've seen that for a ship going from steam to LNG solution, doesn't fit in, or way too complex. And we will have the same with fuel cells. If you want a ship with hydrogen fuel cell, start with a blank sheet and you will find a solution. And I think, Ko, you can
Yeah,
develop on
I
that.
fully agree with you, Renaud. The starting point should be to develop a ship around a new fuel system instead of trying to get a conventional ship and make it fit. And that's also something we did with this Ulstein design. We designed it around the new PEM fuel cells and the storage systems to make it work. And of course, power density is a concern. But it can be solved, especially if you design ships in a slightly different way and make sure that there's sufficient volume to fit the larger power density, then it can work actually. And I think our concept has proven that it can actually work.
Thank you. Next question, and perhaps we'll hear from Raoul first and then broaden it out. What reformer solutions can GE Nedstack provide to the marine market, given that hydrogen cannot be considered, says our delegate, an alternative for deep sea shipping? First, Raoul, please.
Yeah, that's a very good question indeed. I think the first part of this answer is going to be disappointing because neither GE nor Nestec is a supplier of such reformers. The second part of this answer is going to be a bit more positive because we are actually participating also together with GE right now in quite a few application studies where we are validating reformer solutions, and this involves both methanol and methane. And even ammonia could be an option, although we are not working on such solutions right now. There are suppliers of such technology in the market working on the marinization, and I think for where it concerns methane and methanol, there have been previous class approved solutions, and there are submarine solutions that already provide these reformer applications fit for maritime use. What we have done, however, is to make sure that the fuel cell power systems are fit for being powered by reformate, and this is hydrogen coming from a reformation process. So in that way, we have no solutions to offer you. We can connect you with makers that we know of, and we can warrant that our systems are fit to work on reformate.
Thank you. Renaud, please come in.
Yes, one thing in that question is that there is already a consideration, and I think that we can't say that hydrogen can't be an alternative for deep sea shipping. On the contrary, I think liquefied hydrogen is a solution that will work. We will start with short sea shipping for sure. For long range, liquid hydrogen and bunkering solution will come up. I don't think we should go for other alternatives and reformers. It will add processes on board, and there are this come up with more complex systems. In the end, liquid hydrogen for me is the way to go, and it will work. I am sure of that. It has worked for LNG. Why can't it work for hydrogen?
Thank you. One for you, Ko. Ulstein SX190 is said to be designed as per the IGF code. It would be interesting to know what was the process of compliance proposed.
Well, I think at the current stage, then it would be well, lengthy is maybe not a good word, but it would take a process close to a year to get it fully approved with class according to the sort of IGF code and some proposed amendments. And we hope actually that such process would sort of develop into a full set of regulations, which would shorten that compliance period.
Thank you. Could our panel speak to fuel cell short circuit behavior and issues? I could perhaps come to Renaud on this. Would you have a view?
Yes. So indeed, as I was saying, fuel cells are peculiar compared to other power propulsion solution where you need power generation. And on the contrary to many of the other contributors like genset and batteries, fuel cells are not providing the short circuit. So there are specific systems consideration to be there. So indeed, that's a very good question. Fuel cell don't provide the short circuit current. So we need to find other ways to provide this.
Thank you. Perhaps I could come to Raoul on the next one. It's an important one. We get a lot of questions on this issue, in fact. It's around reaction times and capability to handle load transients. They're often considered to be an issue for fuel cells in comparison to conventional power techniques. Raoul, please speak to this issue.
Yeah, it's a very good question indeed. First, I want to take the system level perspective, as Renaud so rightly pointed out in his presentation. There is a coexistence between batteries and fuel cells. So I think that's the first thing to consider. Whenever there's a need for quick responsiveness, typically the battery would be the first unit to turn to. However, fuel cells themselves are also quite responsive. And just like a car, it has a so-called turbo gap. So what determines the responsiveness of the fuel cell is actually how quickly we can mobilize the oxidant, how quickly we can mobilize the air front. In a standard configuration, we would program the blowers, so the air pumps, to supply a stoik which allows for 10% points of the total power range per second. For applications where we need a high responsiveness, we could easily tweak that. You could even overdrive the air blowers in a way that you're capable for instant responsiveness by continuously running at the full RPM rate of an air blower. So this is really a matter of choice. You can increase the responsiveness by having a air front mobilized in a higher stoichiometry, but this sacrifices efficiency. So whenever we tune and we configure the management of these systems, there are always trade-offs to consider. So the responsiveness of a fuel cell, we can really choose ourselves.
Thank you. One of the trade-offs, I guess, that anyone would have to consider relates to sort of degradation and lifetime. Perhaps starting with you, Renaud, but I'm happy to broaden to the other panelists. Could you say a word or two about fuel cell power degradation, and what is the typical lifespan for a fuel cell? Come in, Renaud.
I think this is more a question for Roel, as he's the fuel cell specialist. But yes, indeed, this is one of the, as I said earlier, commonality with batteries. You have to start by oversizing your system, because if you want a 2 megawatt at the end of life of your ship, you need to oversize it to start with. It's degrading slowly. There are some specific numbers that maybe Roel is the best suited to provide.
Thank you.
Yeah, absolutely. Yeah, I'll be happy to comment on that. So a fuel cell degrades with a certain rate, which is normally explained in a microvolt per hour degradation rate. Typically, this is between 2 to 3 microvolts per hour, in which the system loses voltage and by extension loses efficiency. Normally, you would achieve at a number like that somewhere between 24 to 30,000 running hours. And this depends on a lot of factors. It depends on the fuel purity, the oxidant purity. It depends on the exact set point, the amount of start stops. But in general, we could say that within 24 to 30,000 running hours, we would end up at a point that we call end of life. And also this is a bit of a decision. Normally, we would say end of life, or the time to refurbishment, is a 10% loss of the nominal voltage of the system. So
Thank you.
here, it makes clear that you lose efficiency and you lose voltage, and based on your fuel price, you can decide to refurbish earlier or later.
Perfect. I'd like to come to Co. How soon do you think class will be able to go from risk analysis to producing a set of rules and standard classification processes with hydrogen storage fuel cell projects?
Well, that's a bit up to class, of course, and those things take time, but it has actually already been under development for quite some years. So I think it will not be far away in the future, probably some few years until it's sort of final. On the other hand, I want to stretch that if you start a process now for having a hydrogen vessel, you could have it fully classified within a year to run it within class. So there are actually possibilities to do it already. If we start today, then it could be there at the end of next year, actually.
Speaking of timeframes and how long things take, does the panel have a view on the current state of hydrogen infrastructure and how quickly it will be developed? We had reference to chicken and eggs, did we not, in one of the presentations? So perhaps Co, let me start with you, but certainly we can broaden to the other panelists. Come in, Co.
Well, I think the initiatives are there actually. When we actually when I started preparing for this presentation, there was one, and actually now there are 2-3 major ports which actually have announced to start developing a hydrogen backbone or hydrogen infrastructure. So the Port of Rotterdam has announced to make solid work of it within 5 years. Similar, there's a consortium in Denmark which will start developing a hydrogen infrastructure. We've seen in Belgium, in Zeebrugge, similar initiatives. So I think it's actually starting off, and it will be probably will be there in 2, 3, 4, 5 years, and then it probably will spread around the world, a bit similar as LNG. So I think it's actually starting right now.
Okay. Perhaps Renaud, you have a view on this question?
Yeah, I fully agree with what just was said by Co. Actually, it is to be developed, and there are a lot of initiatives. For sure, also support from governments or other similar bodies will play a role. Europe is doing a lot of efforts now, and I think we will see more and more support from Europe, and I hope to see great efforts there. Now, one thing to consider is that also the IMO objectives by 2050 is to reduce by half greenhouse gas emissions. To reach that, you don't need to have a ship that is fully on fuel cell and hydrogen. You can have a power plant that is maybe with a 20-30% power share on fuel cells and the remaining with a genset and batteries, and then you can meet these objectives. So for such a structure, maybe you don't need a fully developed hydrogen infrastructure. So I don't think there are impossibilities here. It is an ongoing process, and I'm sure that we can do something for any ship that is coming. And the more ships that will come into operation with hydrogen, the faster the supply chain will follow.
Thank you. Raoul, your view, please.
Yeah, I think there is a few things that we don't really see, but they're actually there. A lot of the hydrogen that is currently available is actually already in the port domain. It's available as a byproduct from big industrial processes such as chloralkali processes, which are typically located in ports because they need the cooling water and they need the commodities to be supplied. So with reference also to the port of Rotterdam, there's already a great hydrogen grid stretching all the way through Belgium to the north of France, through Antwerp. There are a lot of ports where hydrogen is actually available and could be easily made available as a maritime fuel, either by compressing it in a container or making other ways of refueling stations there. And another thing to ports is that they're also the landing points of where offshore wind energy arrives in the energy system. So they could also bundle, and now we're talking about a future, they could also bundle surplus energy, convert that to hydrogen, and also that could happen at ports. So I think the ports have all the advantages of the hydrogen being available today and the hydrogen available tomorrow. And this is perfectly interfacing, of course, with the maritime domain.
Thank you. Maybe Co can kick us off on this next one, but I welcome the views of others. Converting DC to AC means isolation is relatively easy and lends itself to adding to an existing system. For a new build, however, would a DC grid system be more appropriate?
Well, I think this is actually more a GE power conversion question, but
Come
we
in,
are,
fair enough. Come in,
So,
Renaud. Come in, Renaud.
okay, so as I was stating a bit earlier,
Yeah.
we consider that galvanic insulation is a requirement here. And the other point is that we are talking about megawatt or tens of megawatt power plant in the end for large ships. And today the DC grid for multi-megawatt solutions in high voltage is not readily available. So there are two things: technically, galvanic insulation. So we have these transformers, and DC is not available for large solution yet. So for now, we really recommend the NACE standard with sea-proven references at sea to manage a system with fuel cells.
Fair enough. Raoul, how is NedStack dealing with impurities in reformed hydrogen?
Yeah, this is a bit, into the depths of our electrochemical reactors, and also touching a bit on the secrecy involved and the tricks of the art. I think there are two things that are very relevant here. One is the actual flow fields that are in the bipolar plates. So very pure hydrogen allows for a very thin flow field, whereas reformate requires a bit of a different sized flow field. So to actually guide those gases is one thing, and the other thing is about the robustness of the catalysts. And there is a lot of secrecy involved around that. So that is just to say that we've managed that. We've been tuning that for years, and we've been working with industry grade hydrogen as opposed to automotive grade hydrogen for over 20 years now. And this is where we really differentiate.
Thank you. Some use SW to generate the heat required, but it is limited to a certain extent, and pure water is hard to come by unless a costly water treatment plant is in place. We are surrounded by the sea. Are there solutions to make use of it? Anyone want to have a go at that question?
I'm not sure if I fully understand it. So actually fuel cells are not consuming pure water, they're generating it. So in that way, they're not so hard to come by. They're hard to get rid of. We produce about a liter, half a liter per kilowatt hour, depending on the coolant that we offer to the condenser. So we're actually a producer of ultra pure water. You can make that drinkable, or you can drain it to the sea, whatever you like.
Okay, what about exothermic heat? In order to make more out of less, how do you utilize the exothermic heat generated by the fuel cells? A view on that one?
Yeah, I think the grade of heat that we produce in fuel cells is a bit too low to make steam, and by extension too low to generate electricity from that. But I think there's a lot of vessels out there, passenger vessels in particular, that have a high need for heat, for tap water, for the showers, also for the climatization. And for that, I think the heat of the fuel cell is perfect.
Yeah, I fully
In the
agree.
built environment, fuel cells are used for powering heat grids, and you can do the same on board of a ship. The temperatures are well above the Legionella limits, so in that sense, we fully support any use of heat as a byproduct. Absolutely.
Do come in, Co.
Yeah, I fully agree with that. There are plenty of opportunities to use the excess heat in a ship system, especially for heating accommodation. Well, probably we don't need it for for creating fresh water, because actually the system already creates that itself. So if we go to larger fuel cell systems, there are actually quite a good opportunities to use both the fresh water generated, but also the excess heat in the accommodation part of the ship.
Thank you. An operationally led question here. So from an operational perspective, there's a pilot vessel mentioned, it may stay in the sea for some time without hydrogen bunkering or without the hydrogen bunkering challenge. So the question is, would a self-generated system for green hydrogen fuel be installed on board? Oh, you're smiling, as is
Yeah.
Renault. Who wants to respond? I think you all are actually. Who wants to give this one a whirl?
Well, I would love the energy to be freely available and to be self-generated, but that's not how it works. So no, would it be a hydrogen fuel cell or whatever? We need the bunkering facilities. You can't
Simple as that.
both generate the power and then use it. It's not a ship you are having. It's also I don't know, a plant on its own, plus shipping, plus no, there are too many technicalities here. So a ship needs to be able to sail at a certain speed for a certain operation profile, given that they have the bunkering on board.
Perhaps the panel can help clarify some understanding around PEM efficiency. The understanding of one of our audience members is that PEM efficiency isn't very high at the moment. It's believed to be around 50%, but that could be open to challenge. It's also understood that the existing technology in fuel cells is going to be SOFC, which is going to have a better efficiency. So here's the question. How far is SOFC away from being mature, and are there other fuel cell technologies being worked on which might become available in the near future? Raoul, I see you nodding. Perhaps we should come to you first.
No, I think this is a very good question and a very relevant question. There is a whole scala, a whole galaxy of different type of fuel cells, and all having their best characteristics. They have their own intended use. The 50% isn't too far off. So this is typically indeed the beginning of life efficiency of a total power plant at the relevant working point. So that is fully correct. There's been a great study done by DNVGL on behalf of the European Maritime Safety Authority, in which they have evaluated all different types of fuel cells for being fit for maritime applications, of which PEM came out best and SOFC was best for some use cases. So SOFC typically has a higher efficiency and works at a higher temperature, and that is an advantage from an efficiency perspective. So that is correct. It is up to a few percent, up to almost 10% points better in efficiency theoretically. However, in the maritime industry, use cases are quite demanding. They're demanding from a responsiveness perspective, from a power density perspective, from a lifetime perspective. And here, SOFC is quite challenged. First of all, working at very high temperatures makes them very difficult to be responsive, makes them difficult to service, it makes them very big, and it also makes them very expensive. So here, there is trade-offs involved, and I fully believe that there will be some maritime applications where in the future as SOFC will be better qualified, but still the majority of the zero emission shipping by fuel cell will be based on PEM. That is my strongest belief.
Thank you. Anyone else want to weigh in on that one? Otherwise, we'll talk about cooling.
Yes.
Yes, you'd like to weigh in? Come
Yeah,
in.
just on that topic. Yeah, for now, the most major technology is low temperature PEM fuel cell. So that's why we have made that choice. On efficiency, yeah, 50%, but that's what you have from a diesel engine. They can come up to 60 or just a bit above on board vessels, for instance, because they are able to recuperate a lot of energy out of heat produced. And that's an exercise that we have to do also with the heat available from fuel cells. So I think no, it's we are on par, and the most major technology is PEM fuel cells today.
You
Definitely.
mentioned low temperature. I know that cooling can be an issue at kilowatt systems or with kilowatt systems, obviously with their consumption of energy. How do you cool with megawatt systems? Anyone want to come in on that one?
The shipping industry is doing that for years. Huh?
Yeah,
We have,
it's
that's no
relatively
issue.
easy. No, it's no issue actually, because we normally have combustion engines which generate actually more heat than a fuel cell does. So all the cooling technology is readily available and can be easily integrated.
Last question for our panelists before we take a quick poll and then come to our panelists for their key findings and conclusions. So the last question is, can each of you say something about recycling of the systems, environmentally responsible disposal? Anyone, perhaps Renaud, if you could come in first, and then Raoul, and then Co.
Okay, so recycling, actually the interest of a fuel cell, but maybe that's more for all to say, but basically you can refurbish the membrane and then reuse all the system around. So the lifetime is that of a vessel. On recycling the power electronics, our systems are there to operate the whole lifetime of a vessel. And there are metals and other components that we can recycle, and some other that are to be more specifically looked at. But I don't see any specific or harshest hurdle with PEM fuel cells power installation than compared to others. The main
Thank you.
thing is that you won't have, let's say, fossil fuel that could be polluting when you open the tank somewhere on the beach in India.
Yeah.
Okay, Raoul, very quickly your view, and then Co. We'll take a poll, please.
Great. Yeah, I think polymers age, and that's not something that we can stop. That's just due to physics. And we know that catalysts contaminate. So we know that there are certain mechanisms that determine the end of life conditions of a cell. And we know that we can take these vulnerable parts out and we can refurbish a stack. So making a stack refurbishable, I think that's one of the important parts. Building a catalyst in a way that you can recycle it, that is an important factor. We can recuperate over 96% of the catalyst. And building a balance of plant, which is not limiting the life, but is actually from an industry grade, which allows for any meeting the lifetime requirements of any other engine system on board of a vessel. I think that is what really differentiates. Identifying the life determining factors, isolating them, and developing a refurbishing strategy around them. That is the way to make sure that a fuel cell power installation can last as long as the vessel that it powers.
Thank you. Co, your view, please.
Well, I think actually, well, of course, we have to design also keeping recycling in mind, but I think fuel cells are actually a lot better than fossil fuel systems, and especially a lot better than batteries from a recycling point of view. So we actually do prefer fuel cells and an hydrogen system to the others if we consider recycling of ships.
Thank you. Gentlemen, I'm going to return to you in a moment for your key findings and conclusions. Ladies and gentlemen, stay tuned for that. More immediately, audience, I have a third and final poll for you. The poll will appear on your screen. Just click put your cursor and click against the option that appeals to you. So the question, ladies and gentlemen, is what do you think will be the maritime fuel of choice in 2040? You can see a range of options there in front of you. I can tell you that around half of you see it as hydrogen, approximately 16% say LNG, then ammonia, then methanol, and lagging far behind, around 5-6%, is MDO HFO. Final results shared with you in an article after the webinar. Now, ladies and gentlemen, I come back to our panelists in the order that they presented, and I invite them to share their key findings and conclusions. So, Co, you're up first, please.
Well, actually, I like to repeat the words of Renaud, who said, well, that there is a possibility also for deep sea hydrogen-powered vessels, and I think that's an important takeaway. That it's not only for short sea and smaller ships, but also for deep sea shipping if we design a ship around the fuel and hydrogen system, and that it will be the fuel of the future in that sense.
Thank you. Renaud, if I can come to you, sir.
Yeah, 2 points. Hydrogen is the only solution for zero emission. That's the first point, as I see it. Now, indeed, liquid hydrogen is the way to go, I think, for shipping in the future. And if you want this to be workable for you, you need to start from the blank sheet. That's the main thing. And from there, you have all the possibilities that are ahead of you. You can either go full hydrogen or you can look into hybrid systems. And depending on your profile, we can come up with the right solution.
Thank you very much indeed. Raoul, the floor is yours.
Whenever I talk to actors in the maritime domain, be it ports, be it ship owners, or be it shipbuilders, everyone seems to be in some kind of waiting game. The ship owner is waiting for the shipbuilder, is waiting for the ports infrastructure. And what I learned today is we can escape that waiting game. There are ways to find a way around this chicken and the egg problem. And maybe we can't do 100% zero emission all the time, but there are ways in which we can develop vessels, integrate propulsion systems, and develop fuel cells in which we can do a lot on a zero emission basis, and there's no need to wait for anybody. So my key takeaway is now is the time to start early demonstrators, deployment of these kind of technologies, and everything will go from there.
Thank you. Well, my key takeaway has been this has been an outstanding session. Evidence of that has been the volume of questions and the complexity and the range. So my congratulations to the panel for generating and responding to those. Your dividend, audience, having dialed in live, is of course you will get full answers to the questions posed within a week of broadcast. Our next webinar is tomorrow at 1:30 British summertime. It is on the subject of fuel cells and their key operational challenges, and I look forward to seeing you there. Next week, of course, an entirely new theme. It's offshore wind from the 8th of June. To have an overview of our complete program, please visit the dedicated website, www.rivieramamm.com/webinars. Riviera, for its part, will continue to serve the information that matters to you most. We will do that in a number of ways, through our weekly newsletters, through our magazines, through curated content online that matches your interest, and of course through relevant events such as this. The key thing for you, audience, is that you don't miss out. The way in which you ensure you don't miss out is you register. Please visit our homepage. Honestly, it takes half a minute, and in that way, you're in the loop and you will not miss out on key information and happenings in your sector. More than enough from me. Safe to say thank you once again to our panel for an outstanding job. Our sincere thanks to our partners, Allstein, Nedstack, and General Electric, and our sincere thanks to you for coming from near and far to join us for today's webinar. Do fill in that survey because we will come back to you with the presentations and the answers to the questions. But for now, from me and the panel, wherever you happen to be in the world, please stay well, stay safe. Good morning, good afternoon, good evening, and for now, ladies and gentlemen, goodbye.